light!
Who do I have to talk to to get some lights around here?
Bill Nye the Science Guy.
Bill
Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy.
Brought to you by Reflection. Without it, you couldn't see yourself.
What's going on? It says Ein Siratarabel.
What?
We were fooling with you. I was looking at you through a mirror. See? Light can bounce off of things, like a mirror. Or light can be bent, the way it is when it goes through a lens. Or light can be absorbed, like when it hits something dark. See, we don't see things, we see light bouncing off of things. So take a look at this. It's our light source water box of science. And in here is water with some tiny particles in it. And over here is a very strong light. So light comes into the water box, it hits little particles floating in the water and bounces off of them straight to you. When light hits a mirror, it comes straight onto the mirror and bounces straight off. Watch. Straight on, straight off. That's what scientists like you and me call reflection. Reflection is a word you've probably used before, like when you see your reflection in a mirror. Oh, God. Whew. Sorry. Now, when light hits something, it doesn't always bounce off. Sometimes it goes right through, like when light hits a window. It goes right through the window.
Hey, you kid!
Now, if the glass is curved or bent, the light going through it will be curved or bent too. Watch what happens when I put this bent piece of glass into the light box. See how the light changes direction? See how it's bent? This is what scientists like you and me call refraction. It's from an old word that means to break up, to refract. Refraction is how eyeglasses work, and microscopes, and telescopes, and magnifiers. Now, when light is reflected or refracted, it changes direction. Yeah, I see you.
Sandy and Bud like to work out simple versions of demonstrations they've seen in the science lab at school. The bright sun pouring in through a tiny hole in the tent provided a ray of light. And with a few simple gadgets, they could see how light behaved. They could see the angle of the reflected beam as the mirror was rotated.
Here's an experiment you can do to bend light and be a spy.
All you need is a pair of scissors, masking tape, 2 mirrors, and an empty milk carton.
Okay.
First, cut the top of the milk carton off like this. Then, cut 2 holes, one in the top right here, the other in the bottom right here. Place the first mirror inside the milk carton like this. Tape the other mirror in the top like this.
Light comes into a periscope here. The top mirror bounces the light down through the milk cartons to another mirror which bounces the light into your eyes.
When it's all done, it should look like this.
Oh, that's a nice one. Very good.
You can use your periscope to see over things.
You never know what you might find.
Hi, I'm Penn, and this is my partner, Teller. We're Penn and Teller. Light travels in a straight line unless it hits something or is pulled by gravity. Of course, it goes faster than that in the real world. When light hits something, it can be bent, bounced, or absorbed. Or it can just look really stupid.
This is your searchlight. It's got a bright electrical spark. The light from the spark bounces off a mirror And the mirror is curved just so that the light will bounce off of it and go straight into space. Do you see anything yet? Probably draw a crowd.
Science! Science!
As you may know, scientists like to think of light as traveling in waves. So let's say that this marching band is like a beam of light, and each row of marchers is like a wave of light. People in marching bands keep an eye on each other. That's how the band stays in formation. When one side slows down, the whole row turns. In fact, that's how marching bands turn. So when the marching band hits that little hill over there, one side of it slows down, and that makes the whole formation, the whole wave, turn. When waves slow down, they change direction. Isn't that cool?
I can turn on the TV over there by pointing the remote control over there.
Hello, I'm Bill Nye. I'm a human. I'm Bill Nye.
Watch me change the channels.
I'm Bill Nye.
Gotta hear from Simon LaRue in Kalamazoo.
Bada bing, bada boo.
Pretty cool, huh? That's because the remote control uses infrared light to tell the TV what to do. This white piece of paper reflects light pretty well, so we can use it to bounce infrared light from the remote control to the TV set.
Now, if you use a black piece of paper, the light won't bounce off, because black paper absorbs the light.
The hula hoop stays held up by the swaying motions of your heavy hips.
Okay, channel line 11. Channel line 11.
It's a channel 11.
Channel line 11.
I'll just turn it off. Move your hand. Channel 11.
Coming soon from Photon Pictures. In the Old West, things were different. In the Old West, straight-shooting ruffians ruled.
I'm as straight shooting as light is. No, you ain't. I'm as straight shooting as the light is. Or not. And two or not.
Photon Pictures presents Lights Out at the IC Corral. A place where straight shooters ruled until she came to town.
Try your beam.
Don't miss Lights Out at the IC Corral. Coming soon at the speed of light through a projector in a quasi-multiplex mini-mall conglomeration near you.
The way a lens is curved affects how it bends light. See, the light from this candle is going straight into this lens. But because the sides of the lens are curved, the light gets bent. So look, down here we have a blurry patch of light. So I move the screen in, right here, at this point, that's where the candle flame is in focus. But look, it's upside down. It's all caused by the sides of the lens being curved. Now, if a lens is curved in like this, we say it's concave. Now, concave lenses make things look smaller and farther away, like they're in a cave. Okay? Okay? Ha! Now, if the sides of a lens are curved out like this, we say it's convex. Convex lenses make caves look bigger.
Huh?
Hold on, I messed that up. They make things look bigger. That's right. That's it. The convex lenses, where the sides get bigger, they make things look bigger. That's it. That's what it is. Now, you have convex lenses with you all the time. They're right here in your eyes. Ooh. Anyway, convex, concave. Like a cave, like a...
Like a vex?
Sandy said he could always remember concave by thinking of a sort of a cave, hollow. Convex is the other way.
When we see objects in a mirror, we're looking at light that's bouncing off the object, then bouncing off the mirror, and then coming into our eyes. Here's the thing. Parts of the object that are on the object's right stay on the right. Parts of the object that are on the object's left stay on the left. It's a mirror image, for crying out loud. See, we're facing the reflection, not the object. So that's why we have ecnolibmus. Ecnolibmus.
Hi, I'm Penn, and this is my partner, Teller. We're Penn and Teller. Did you ever, I don't know, look at yourself in a spoon? Well, if you look at yourself this way, you're right side up. But if you look at yourself this way, you flip upside down. Why is that? Well, let's look at the spoon sideways. See, the upside down way, the light waves come in, bounce, and cross themselves, making you look upside down. See?
When light bounces off of a flat mirror, it bounces off at the same angle that it hits. In fact, that's what light does with any mirror. But if the mirror is curved, it's making a slightly different angle with the mirror at different places. So it looks weird. Like, totally weird, man. Like, you could, totally, freak out. Whoa! See that can? Right there on the bottom. I'm gonna reach for it with this grabber arm of science. But watch what happens. As I aim for the can and squeeze, I miss. No, I'm really trying to get it. Here's what's going on. The light bouncing off the can is changing directions as it goes through the surface of the water. And so the can looks like it's in a slightly different position than it really is. And I miss. But if I compensate for the refraction of light, I can probably get it. I'm gonna aim a little lower. Got it. You want some?
Here's a light trick that doesn't need mirrors. Put a penny in a pie pan. Now move back so you don't see the penny. Don't move, because I'm going to pour the water in. It's okay if you make a mess. Pretty cool, eh? See, light's always bouncing off the penny. But when you pour the water in, it makes the light bend. And the bending of the light makes the penny reappear. But the penny didn't move through all of this. But don't take my word for it. Try it.
This magnifying glass is making my eye look big. Now, why is that?
I don't know.
Please consider the following.
Okay.
When light enters something like air, water, glass, or plastic, it slows down a little. And when it slows down, it changes direction. See how one eye is lower than the other? See? Take a look at this. Here are 3 straight beams of light. When they go into the piece of plastic straight, they come out straight. But if the plastic is tilted, the beams of light get tilted. See, they change direction so that they come out this side offset. Now, what would happen if the piece of plastic didn't have straight sides, but had a curved side, like a magnifying glass? Well, the light would change direction, right? Because the surface of the plastic is curved, each beam of light enters the piece of plastic at a slightly different angle, and it changes direction a slightly different amount. Oh, look, over here the beams of light come together at a single point. This is called the focal point. Now, what about the magnifying glass? Well, suppose your eye were over here, and light from the room were bouncing off of your eye and going through the piece of plastic this way. Well, then, the small area at this end would be spread out over a large area on this side. Your eye would be magnified. Ha! Thanks for joining me on Consider the Following.
Clearer than a corner office window. More focused than an automatic camera. Able to read fine print with a single glance. It's Lindo Lens. Disguised as mild-mannered bank teller Stephanie Astigmatism, Linda uses a variety of concave lenses to bend light entering her eyes whenever things get blurry. Linda Lens, defender of sight, focus, and the 2020 way. Today's episode, Hocus Pocus.
Try this. Get a glass of water and a pencil. Stick one end of the pencil below the surface of the water. And look, the other end disappears. You can only see the end of the pencil that's underwater. That's because the light is bouncing off the bottom surface of the water. It's what we call internal reflection. It's reflection inside. The same thing happens in this plastic rod. I'll shine the small laser in one end. Watch. Most of the laser light stays in the rod and doesn't come out till it gets to the other end, see? Pretty cool. Anyway, this is called an optical fiber. And that's how modern telephone calls and computer information are sent all over the world. The telephone call or the computer information is changed into a beam of light, sent down an optical fiber, and then decoded at the other end. Oh, excuse me. Hello?
Billy boy?
Oh, it's my mom. Tell me, you guys go ahead. I'll catch up with it.
I'm Carol Tights, and I'm an orthopedic surgeon, and I'm just about to do some surgery on somebody's knee.
I believe I've heard it playing basketball. Tore the medial meniscus cartilage in my knee. They're going to snip out the bad cartilage.
Well, actually, when I was training, I trained to cut the knee open to do what we're going to do today. And then since then, they've developed the fiber optics, and we've been able to look inside the knee without cutting the knee open. This is the lens of the arthroscope, and the camera will go right onto the scope like so. And now all the images are going to be up on a TV screen. Bill, that's your kneecap up top, that white thing. Yeah, normally I don't think you could look inside of the knee. It would probably be fairly dark, but we've got this incredibly bright light coming into the knee through the miracle of fiber optics. And that's what's making the inside of the knee so it looks so bright and white and allows us to put it on video. Let's get a still of that. We usually take stills and he'll give them to Bill when we're done. So he has them for his Christmas cards next year.
It's actually a pretty neat experience, except for having to pay for it, I guess.
Let's look at internal reflection in the light box of science. See, the light beam is coming into the box and hitting this mirror. As I rotate the mirror, the beam starts to bounce off the surface of the water until there, look, internal reflection. It's pretty cool.
Want to see light bend? Watch. Take an empty soup can and poke a hole in the bottom. Be really careful or have an adult do it for you. Put your finger over the hole and fill the can with water. Now put a flashlight over the top and turn off the light. Take your finger off the hole, and look, you can only see light where the water hits. The light stays inside the water, and when the water bends, the light bends too. Science.
It's hot. It's hot enough to grow cacti. That's because this is a greenhouse. It's a building made of glass. And the glass acts a little bit like a mirror. See, all different kinds of light energy beam down from space on top of the greenhouse. The glass reflects the short wavelength ultraviolet back off into space. The long wavelength infrared, the heat, gets trapped inside, and it gets hot. Visible light, the light that we can see, goes right through the glass, and it hits the green plants. The plants use the visible light to help them make food. Now, while they're at it, they give off heat. That's infrared light, and that's trapped by the glass. And that's what's keeping it warm in here. It's not warm in here, it's hot. It's hot in here. It's like 33 degrees Celsius. I mean, we're growing cacti in here, for crying out loud. It's a greenhouse.
Science.
Light can travel straight, light can move and bounce or absorb when it hits a funky groove. and hold on tight. We're gonna bust a move with something called light, which travels in a straight line, as you can plainly see, unless it hits something or is pulled by gravity. And this might be a surprise. When light hits something, it bounces back to our eyes, but some light is absorbed, as you probably know. White light contains all the colors of the rainbow. A red thing absorbs every color but that hue: orange, yellow, green, indigo, violet, and blue. But the red light bounces back, and that's the color we see, whether it's a fire truck, a sweater, or a skin duck knee. Now hold on, because I'm not done yet. You know, light can bend if it goes through something wet. Look at this pencil and you'll have to agree, light bends if it passes through a different density. Light can travel straight, light can move, bend, bounce, or absorb when it hits a funky groove.
The light that bounces back is the color that we see.
Light can travel straight, light can move, bend, bounce, or absorb when it hits a funky groove.
The light that bounces back is the color that we see.
Light can travel straight, light can move, bend, bounce, or absorb when it hits a funky groove.
The light that bounces back is the color that we see.
Well, that's our show. Thanks for watching. If you'll excuse me, I've got some waves of light to bend. I'll see you next time light bounces off of you and refracts through the lenses in my eyes. See ya. Hey. What?
Produced in association with the National Science Foundation.
Hey, are you listening to me?
Mike's the sound of it right there. Okay, rolling.
Hey, are you listening to me? Hey, are you listening to me?
Rolling.
Okay, how's that?
Okay, come. Okay, that's good. Rolling.
Hey, pay attention.
Try it again.
How about throw this one, Bill? Oh, it's just so weird, man.
Okay.
Okay. Rolling.
It's like so weird, man.